Okay, I'm going to walk you through how to analyze a system that has multiple objects in it, and especially when they are moving in different planes. So for this example, I'm going to include friction. If you are at a point and you haven't talked about friction yet, just completely ignore any recognition to friction by me. So just kind of cross those out and you do the rest of the problem. Just make all those values 0 and you'll be good to go. So just a heads up in case this comes out of order for you. But let's talk about how I go through this. There's multiple ways to solve this. You can do two systems and two unknowns and do it that way, or you can do some tricks. So I thought I'd show you the tricks that I use to make these problems a lot easier. So whenever you have a system that has multiple objects and you're going to end up accelerating in multiple ways, so for example, this guy is going to end up accelerating in this plane while this guy is going to be accelerating in this plane. So it's not the same plane, so things can get a little dicey. So here's how I handle the situation. Normally we say draw the force diagram off to the side and work with it there. Here I'm going to say I want you to draw the force diagram directly on the picture. Okay, so we're going to start there. So let's go with green. So I'm going to draw my forces and I'm going to label these. And again, this is where on notation really helps. So I'm going to do, this is the force of gravity on the 3 kilogram object. I would have the force of tension here. I then have the force of tension here. I have the force normal and the force of gravity on the 5. I'm labeling this with the 3 and the 5 so I don't get those two confused later on. And then I've got a force of friction. And then of course I should make my tick marks because it's not accelerating. So it's accelerating only in this plane, which actually changes directions halfway through. So once I do this, I could pick this as my system, draw some net force use some net force equations, and then pick this as my system, do some more net force equations, and then I'd have, multiple equations, multiple unknowns. I could solve it, things like that. But I don't like doing that. I like being a little more efficient. So what I'm going to do is I'm actually going to pick everything as my system. So let's see, fun color day, I guess. Yellow is a horrible choice. Blue, we'll go blue. So I'm going to pick everything as my system. I choose both objects. But now since I want to find the tension in the rope, well, if I choose everything as my system, that's not an option right now. But I can find the acceleration of the 5 kilogram block, because if I know the acceleration of the 5 kilogram block, I also know the acceleration of the 3 kilogram block because they're attached to one another. Now, I'm going to do a little trick here, and I'm going to redraw this over here as a new force diagram. And I'm just going to manipulate this so that my acceleration is in the same plane. So stick with me for a moment. So I've got my 5 kilogram block. This is going to look exactly the same as it did over there. So I'm just transposing some stuff. Fg on the 5, force of friction. I'm going to ignore tension because it's an internal force now. But I am going to keep the rope there just for kind of visual purposes. So then there's my 3 kilogram block. And notice I've drawn it to the side because what I'm basically doing is I'm taking this and I'm pivoting it upwards. But as I do that, I have to keep the forces relatively in the same plane. So if I twisted this up, that means that the force of gravity is now moving sideways instead of pulling down. So now what I have is instead of accelerating in 2 planes, I am once again, where I'm happy, accelerating in only 1 plane. So the whole thing's accelerating in this way. And then I have chosen all of this as my system to work with. So now I don't have to do, weird multiple accelerations and directions. It's basically now an old school physics problem. So I will approach it as such. So this means I'm going to make 2 net force equations, sum the forces in the x equals ma, and sum the forces in the y equals ma. Okay, I can approach this in any order I want. I am going to approach this one first simply because I know friction's involved, and from experience, balanced forces. Sure you yelled at me for that. Then I know that these 2 forces are going to be balanced, and friction is going to rely on this guy. So I kind of need to know that. So let's do that now. So force normal minus the force of gravity acting on the 5 equals ma, and then Fn minus 5 times 9.8 equals 0, because we have no acceleration. So that means that the normal force is equal to 49 newtons. All right, so that's a fun thing to know. So then I'm going to go over into the x-plane, and I'm going to set up my net force equation. So now I'm going to write Fg of 3 minus the force of friction equals ma. Now here's where some students get a little confused, and that's when I do the Fg of 3, this is where the subscripts really help. This is the force of gravity that's only acting on the 3. A lot of students will say, hey, I want to use, all of it and things like that because this is gravity pulling everything. No, this is force of gravity only acting on the 3 kilogram object by Earth. So again, that on by notation, really helpful. Even if you don't write it, you kind of have to mentally be able to use it. So that means that this is going to be 3 times 9.8 minus the force of friction. I'll replace that with mu Fn. Again, if you have no idea what friction is or what this equation is, just ignore it, make this a 0, and ignore the rest of my talking. M, this is always the mass of your system. So what that means is it's everything added together. So it's not just 3 we're going to use as our mass. It's not just 5. We're actually going to use an 8. Okay? So keep that in mind. So this is going to be 8 times my acceleration. So now I'm going to bring this in here. I did mention that the coefficient of friction, or at least I wrote it down, I don't think I mentioned it, is 0.2. So we've got 3 times 9.8 minus 0.2 times 49 equals 8a. So now all we have to do is our algebra. So if we do our math and solve, we get 2.45. So that is our acceleration. So we have done that first part, or I should say the second part of the problem, by finding the acceleration. So now, if I want to find tension, I can now actually go back to my original picture and I can say, I know what all of these are. These are all 2.45. So now, to solve for acceleration, solve for tension in the rope, then I can pick either one of these as my system. I can either choose the 3 or I can choose the 5. So whichever one you want to pick, it's all good, no problems. In fact, I'm going to solve it both ways just to show how it doesn't really matter which one you pick, you'll still get the same answer. So I'm going to scroll down a bit. I'm going to lose a little bit of that picture, but not really a ton. Actually, let's bring a little back. Let's bring a little back. I can work with this. I can work with this. Okay, so I'm gonna need some more colors out here. What color feels good today? I'll go green. Green. We haven't done green in a while. Okay, so let's just do it for the 5. So this is for the 5 kilogram block. And if we look at just the 5, I'm going to redraw that force diagram, a little rough. So I've got force of tension, force of friction, force normal, force of gravity, and again, those are balanced. So I'm going to do a net force equation. Sum the forces in the x equals ma. I've got then force of tension minus the force of friction equals ma. And so now I can do some substitution. So force tension, I have no idea. That's what I'm solving for. The force of friction, I do know it. I can use it from over here. Okay, so I'm not going to go through all the steps again. So I just happen to know that from, because it has not changed. It's not like it's a different object. So the force of friction is 0.2 times 49. And then the mass of my system, that's just the 5 kilogram block now. And we now know its acceleration from over here. So 2.45. And so now I can just do the math, and I can solve for the force of tension to be equal to 22.05 newtons. Okay, so I could say, hey, I got now the tension I was looking for, so I'm really good to go. But I could also say, you know what, I'm human, I make mistakes, let's double check this. And so that's what we're going to do. We have 2 objects, so we can do two two net force equations. So I'm going to use the 3, and I'm going to do a force diagram for the 3 kilogram object to see where that takes me. And here I've got force of tension, force of gravity. I'm going back to the initial setup. I could actually use this setup over here if I want to use left and right, but I figure I'll go back to the original setup. So now I'm just going to sum the forces in the y-plane, set that equal to ma. So I've got force of tension minus mg equals ma. What happened there? And substitution, so force of tension minus 3 times 9.8 equals 3 times, and now since we're going down, this is going to be a negative 2.45, so don't forget to keep those signs all working for you. And then when I solve for this, I get the force of tension is equal to 22.05 newtons. So that way you can see that either way you solve this, you can make that connection to say that this answer and this answer should be the same because it's the same rope. One rope can only hold one force of tension. Basically, tension through a rope is just a way to transmit a force. So the 3 acting on the 5 is exact same as the 5 acting on the 3. Newton's third law, it's real, believe it. So this way, you can solve it either way or double check yourself if you've got an assessment, things like that. So hopefully that shows you how to handle two objects that are accelerating in different planes and how to kind of manipulate them to make it more palatable. So enjoy life and enjoy physics.